Dear students, in our course Linear Algebra, Unit 2. In this unit, we are going to discuss properties of matrices and some real matrices and complex matrices, solving system of linear equations, and we are going to find fundamental subspaces of a matrix and a fundamental theorem. Now, in this one, first lecture, oral ninth lecture of Algebra of Matrices. Already you know the properties, algebra of matrices. We recall again. First up, we define what is the matrix. The matrix definition. A matrix A over a field, some field, any field over a field F is a rectangular array. It's a rectangular array of scalars, usually represented of the following form. Generally, we are using matrices form like this one, or like this one. This is a matrix representation. Sometimes we are writing the elements Aij or capital A. This elements in notation or Aij. Sometimes you are writing matrix A equal to this Aij, that elements. Suppose if you write M by N, that I is varying from 1 to M, J is varying from to I to N. That's M by N matrix. The element we represent sometimes Aij or capital Aij. That means ijth element or sometimes Aij or Ai comma J. It's a notation. This one is called the ijth entry or ijth element. Suppose if I write suppose A, suppose 2 comma 3. Suppose 2 is 2 comma 3. That means second row, third column element. This one. If you represent 2 comma 3, second row, third column element. That ijth entry or ijth element in the ith row and ith row and jth column, second row and third column like. The ith row is represented by ai. This is notation. And jth column is represented by colon comma j. Nth I comma colon. This one. We denote the matrix by simply written like this one. Represent the one, this one. I written again. This is simply written A is equal to the square bracket Aij M by N matrix. This is a definition of matrix. Already you know these elements field. Maybe these are, suppose these all elements are real numbers. This matrix is called a real matrix. But it's a complex matrix. So that one. It depends on field. Now some remarks. In the above representation, we observe the following. What are the observations? The size or order of A is M by N. As it has, we read as this one M rows and N columns. If we read M by N, it represents M rows and N columns. That M by N matrix means it has M rows and N columns. The horizontal arrays of matrix are called rows. Horizontal are rows and the vertical arrays of matrix is called column. That horizontal is like 1, 2, 3. This is a row, first row. Suppose 4, 5, 6 is second row. And the vertical is called columns. Already you know these things. One write A belongs to M comma N. What that means? It means A is an M by N matrix with entries from the set field. With entries from the set field. If M equal to N, then we write A belongs to Mn. M means that is square matrix. The rows and number of rows are same as the number of columns. Another property. A matrix with exactly one element, sorry, one column. It's exactly one column is called a column matrix. Exactly like one column. 1, 2, 3, like this one. This is a column matrix. This is a 3 by 1 we represent. Exactly one column matrix. Or a column vector. You can represent column vector or column matrix. A matrix with exactly one row is called a row matrix or a row vector. Like this one. Row vector or row column. A row matrix or row vector. The entries of the matrix can be numbers or functions or polynomials and even matrices itself. See, sometimes we represent like this one. These are the matrix. Suppose 1, 2, 3, 4. So, represent itself, it's a matrices like some sub matrices of this one. We can write. That means the entries may be numbers or functions, any function or polynomials, and even itself it's a matrices. This is matrix. Already you know these things. Next, a one by one matrix is called scalar. Today's scalar, and it's treated as a one by one matrix. Suppose an element 2 is there. This element is a scalar. This one you can itself as you can treat as one by one matrix and is treated as such. The one by one matrix is also called a scalar. Yeah. Now some definitions. Let A is a B on M by N matrix with A is a belongs to some field. Then A is called a zero matrix. It's denoted by zero. Zero matrix is denoted by zero. Order is mostly clear from the context. So depend on that one. Suppose if M by N matrix means all M rows and N columns are zero. That means it's a context. It's a clear remove. If A is zero for all I and J, that means suppose A is O is 3 by 4 matrix means 3 rows, 4 columns. All elements are zeros. For example, like this 2 by 2 zero matrix, 2 by 3 zero matrix. Next, then A is called a square matrix. Square matrix means already I told you this one. The number of rows same as the number of columns. It's represented by A belongs to M and F. Like A belongs to M and F. That means a square matrix. If A is said to be a diagonal matrix, denoted by diagonal A11, A22, A. Means if A is 0 for all I and J, like means suppose 3 by 3 matrix. Diagonal matrix means this A11, this are remaining all are 0. A22, 0, 0, A33. Only these diagonal elements are 0. Like this one, if write 1, 0, 0, 0, 2, 0, 0, 0, 4. It's a diagonal matrix. It's also represented diagonal of A11, A22, up to AN. Or this is the 3 by 3 matrix. You can write diagonal 1, 2, 4. It's a diagonal matrix. Yeah, for example, the zero matrix also diagonal itself. That means it's a zero matrix, diagonal elements are 0, 0. And 3, 2. These are diagonal matrices. The entries A11, A22, N constitute the principal diagonal of A. This also is the remaining also, this are also you can say diagonal. This is a lower diagonal. But these elements are called principal diagonal. That be A11, A22 up to so on AN are principal diagonal element. Now, this is diagonal. This is a identity matrix. It's called the identity matrix denoted IN. And short form, just simply we write I. But, this IN means represent order. I2 represent order. This I2 means 1001. Like this one. Yeah, like already given the example. For example, I2, I3. This one. The matrix A is called Ki. For some K belongs to F. Is called scalar matrix. That means all are scalar matrix. Yeah, that means 2 0 0 0 2 0 0 0 2. This is scalar matrix. The same as 2i. It's called scalar matrix. A is said to be an upper triangular matrix. It's upper triangular means below diagonal elements all are 0. Generally we write this A11, A12, suppose I'm taking 3 by 3 matrix. A21, A22, A23, A31, A32, A33. A 3 by 3 matrix. See, it's a upper triangular means these above elements are 0. That means this I is more than J, it's a zeros. Yeah. Where is I is more than J? This is below diagonal elements. These all are 0. Upper triangular matrix. Next, a lower triangular matrix. A is said to be lower triangular matrix if A is equal to 0 for I less than J. J is more than I. Where it's J is more than I? Both the diagonal elements. The lower triangular means above the diagonal elements all are zeros. Suppose A is said to be triangular. It's a triangular means it is either upper triangular or lower triangular matrix. So sometimes strictly upper triangular. Strictly upper triangular means the diagonal elements are also zero. Strictly upper triangle means this total lower triangular, sorry, below the diagonal and diagonal elements also zero. In that case, it's called strictly upper triangular. If to represent Aij equal to 0 for I less than or equal to j, that means diagonal elements also 0. In this case, it's called strictly upper triangular. Similarly, strictly lower triangular means Aij equal to 0, Ai less than or equal to j. That's strictly lower triangular. Yeah, for example, this is an upper triangular example. This is upper triangular. Below diagonal elements are 0. The diagonal may be 0 or non-zero. That doesn't matter. But below diagonal elements all are must be 0. This is the upper lower triangle. This is below diagonal. Suppose this term also 0. This I also 0. A strictly lower triangular matrix. And this matrix 0 and I are upper as well as the lower triangular matrices. 0 and identity. It's upper as well as lower triangular matrices. Now, equal matrices. When you say two matrices are equal, two matrices A and B, Mn and Mn, so same order matrices, said to be equal if Aij equal to Bij. That means each element is same. For each I is equal to 1 to M and J is 1 to N. Or in other words, we can say two matrices are said to be equal if they have the same order and their corresponding entities are same. Same order, suppose 1, 2, 3, 4. It's equal means it's also 2 by 3 order. Each element also same. Suppose if you write A, B, C, D, when is these are equal? A equal to 1, B equal to 2, C equal to 3, D equal to 4. That means the same order and corresponding entities also same. Okay, this one. Suppose A equal to B. If A equal to 2, 3, 4, 5 and B equal to A, B, C, D. Find the ABCD values. If and they're given A equal to B. If A equal to B, so find B. B means and B when A equal to B. It means A equal to B, you can find that both are same, get same elements. But they are given some relation also. Suppose A plus B is given or whatever given, and equal to condition means it's given A two matrices are equal. The same order and the corresponding elements are same. You have to keep in mind. So corresponding elements are addition and scalar multiplication. Already you know the addition and scalar multiplication. What is addition? Let A and B these two matrices, M by matrices. The sum of A and B denoted by A plus B. It's defined to be the matrix. This addition also you get another matrix, some C. C belongs again M by matrix with Cij equal to Aij plus Bij for all I comma j. That means suppose 2, 3, 4, 5. Suppose A B equal to minus 1, 2, 3, 4. Or A plus B equal to adding these two matrices. 2 minus 1, 1. 3 plus 2, 5. 4 plus 3, 7. 5 plus 4, 9. Like here this is C11, C12, C13, C14. It's a B1, sorry, C21, C23. Same as the C11, C12, C21, C22. You know C11 equal to A11, B11, A11, B11. C2 equal to A22, B22. Like this. So scalar multiplication. The scalar product of K belongs to F with A. K is any number in field denoted by Ka equal to Ka. This one K into Aij or Aijk or same as AK, A into K. Ka is same as the A into K or Ka. Both are same. That means each element we are multiplying. What that means? Each element multiplying. Suppose Ka. 2A means, suppose if A equal to 3, 2 minus 1, 3. What is then Ka equal 2A equal to? So means you have to multiply each number. 2 into 3, 2 into 2, minus 1 into 2, whatever. 2 into minus 1, you can 2 into minus 1, 2 into 3. That's same as 6, 4, minus 2, 6. Not only particular, you have to multiply each element. 2 into minus 1. Just scalar. Here 2 is the scalar. A matrix multiplied by some scalar, some non-zero scalar. If you multiply with 0, you get 0 matrix. Some non-zero scalar. The properties of matrices. Let A comma B comma C belongs to M by N matrices. Then commutative property. This addition satisfies commutative property. A plus B is same as the B plus A. Now it's associative property. The addition also satisfies associative property. Matrices satisfy associative property. Already you know last unit we discussed the set of all matrices form a vector space. Vector space means it satisfies commutative, addition property, and identity also there. Zero identity and inverse property also there. Already you know this one. Again we recall that one. If A plus B, additive inverse of A means the negative matrix. B is the negative matrix. It's a property already we discussed again. Now for the transpose of matrices. Transpose means let A is M by N matrix. The transpose of A denoted A transpose. It's denoted by A transpose. A capital T, A power T is an N by M matrix. It's M by N matrix. You get transpose is N by M matrix. That means Aij is transferred to Aj for all I comma j. For example, A is equal to 2, 1, minus 1, 3, 0, 2. It's a 3 by 2 matrix. For the transpose, you get 2 by 3 matrix. The first row transform to column. 2, minus 1, 0, 1, 3, 2. This is the 2 by 3 matrix. Yeah, that means Aj transpose to Aj. We write A11, A12, A13. What A21, A22, A23. This transpose, this A11, A21 is it's interchange this one. Aij is same as Aj. The one is same is transposed to one like that. Aij is same as the Aj. Then rows is transformed to columns. Suppose if it is a transpose of transpose. Suppose again if transpose this one, we'll get again transpose. We'll get this 2 minus 1 0. First row transform this column 1 3 2. Same as A. That means transpose of transpose matrix is itself. Now properties of transpose already you know this A plus by any two matrices and K is any scalar. Then A plus or minus B is transpose same as the A transpose plus or minus B transpose. No, already no. This one A transpose of A transpose is itself. Now K into A transpose same as the K into A transpose. It's a not change. Suppose if you multiply 2A transpose 2A or 2 into 2 transpose into A transpose like that one. The 2 transpose same thing. Or you multiply with the transpose or after transpose multiply. We'll get both are same. First multiply, suppose multiply with the 2 and transpose. That's a 4, 2, minus 2, 6, 0, 4. Transpose. This equal transpose is 4 minus 2, 0, 2, 6, 4. Or first transpose and multiply. If multiply this one again we get same. The same as we'll get 2 into A transpose. Now on our definitions. Suppose A is n by n square matrix. with Aij belongs to F, then a matrix A is said to be symmetric. Symmetric means A transpose same as the A. Already you know this one. And Aij same as the Aji for all I and J. That means A11, A12, A13. Suppose 3 by 3 matrix. This also same A12, A22, A23. This also same A13. This also A same A23, A33. Whatever these two elements are same, these two elements are same. These two elements also same. Aj is same as the Aj. In that case, the matrix is called symmetric. Now a matrix A is said to be skew symmetric if A transpose equal to this is minus A. Minus A. If that is minus A means Aij same as the minus Aj for all I comma j. That Aij is same as the minus Aj. You'll get if I2 is there, it should be minus. Now trace of a matrix. Trace of it is denoted by trace of A. This one. Trace means sum of diagonal elements. Suppose 2, 3, 2, 3, 4, minus 1, 2, 0, 2, 3, 5. Suppose A is equal. What the trace? Trace of A equal to. Sometimes you write TR of A or trace. Whatever you write, both are same. This trace equal to sum of diagonal elements. 2 plus 2 plus 5. 69. This is the one. Now, one more thing. The diagonal elements of skew-symmetric matrix are 0. Diagonal elements of skew-symmetric matrix are 0. It's simple. It's pretty simple. Let A be a skew-symmetric matrix. Symmetric matrix. A skew-symmetric matrix that is A transpose equal to minus A. That implies Aij equal to minus Aj for all I comma j. It implies Ai is equal to minus Ei for all. Because we require only diagonal elements. That is for all I. That means I is equal to j. Only diagonal elements. That implies this means 2 Ai equal to 0. 2 is non-zero element. That means Ai equal to 0. It implies 0 for all I. Yeah, equal to 0 for all I. That means A11, A22 all are 0. That is diagonal elements are 0. If you say matrix is skew symmetric, diagonal elements must be 0. For example, suppose A is equal to 2 minus 1, 0, 2, 1, 0, minus 3, minus 2, 3, 0. This is a 3 by 3 matrix. I can check it. For the A transpose equal to 0, 1, minus 2. First row as a column. First column as a row. Second column minus 1, 0, 3. Third one is 2 minus 3. Third row. This one. The A transpose this one. If you take if you take minus common in this one, if this is 0, minus 1, 2, minus 1 plus 0, minus 3, minus 2, 3, 0. The same as A. A transpose is same as A. So if any this development is non-zero. It's a non-zero. Suppose if this element is non-zero. Suppose if you take 2. When you take 2 here, if you take minus common, you get minus 2. It's not the same as the A. That's why diagonal elements are always 0. One more property. Theorem this one. Every square matrix, already you know this one, every square matrix uniquely expressed as sum of symmetric and symmetric matrix. Sum of symmetric and skew-symetric matrices. Every square matrix you can express as sum of symmetric and skew-symmetric matrices. Already you know. Suppose let A be a square matrix, any square matrix. That means we can write. I am writing this one 1 by 2 A plus A transpose plus 1 by 2 A minus A transpose. You can check it. This one half A. This is 2A by 2 is a A. Half A transpose minus half A transpose. This cancel that A equal to A. Both are same. But this is P. Suppose this is Q. This is a PQ are symmetric. You can check where P equal to what the P transpose equal to. Okay. P transpose equal to 1 by 2 A plus A transpose whole transpose. 1 by 2 A transpose plus A transpose of A transpose. Just now we see properties. A plus B transpose same as the A transpose plus B transpose of A. A transpose of transpose itself. A transpose. This A transpose. This is the A. This same as 1 by 2 A plus A transpose. This same as the P. It means P is symmetric. This is a symmetric matrix. Observe here Q. Suppose take Q transpose of A minus A transpose whole transpose. This is equal to of A transpose minus of A transpose of A transpose. This is equal to of A transpose minus A. If take minus common here, A minus A transpose. The same as the minus of A minus A transpose is the Q. That means it's a Q symmetric. Q symmetric. That means a matrix, a square matrix, we written as sum of symmetric and skew symmetric matrix. This expression is unique. This expression is unique. Suppose you take A equal to some RS, R plus S. If you take R transpose, we'll get same as the itself, we get same P. And S transpose also, so we get same itself Q. That means every square matrix we can write as sum of symmetric and skew symmetric uniquely. Already studied in PUC, again we recall this one. Now take any square matrix, you can try this property. That means every matrix you can write this way. You can take any example and try this property. Take any example, any 3 by 3 or 4 by 4 matrix. Now write sum of symmetric and skew symmetric matrix. This is like take exercise. Now I am stop here. Thank you.